Hi, I'm Peyton Kilborn, and this is my work for Lab 2 of Physics 2212, revisiting the charge tape. So we had the same experimental setup of placing two, two pieces of tape on top using friction to charge the top one, and then repeating that to create two the same charge and setting them atop each other and balance out electric force and gravity and the force of gravity. And then and that was our experimental setup. And then the purpose of this lab was to use common laboratory materials like the tape to measure the magnitude of the charge analytically and for better understanding the concepts of electric fields. And some key ideas that would help us in this is that when the tape is stationary, the the y forces from gravity are the same as the y forces from electric field, and then opposite charges attract and like charges repel. And then we also have to add in that charge is dispersed over the entire charge surface, and these come from our lectures. So relevant equations, we start with the static equilibrium equations, which allow us to say object is not in motion, there are no net force on it. Coulomb's law, here we get the force from the electric field, and then law of universal gravitation. Here we get the force of gravity. Here's our lab setup. You can see two pieces of tape there. All right, and then for coding, we start in the top left with some physical constants, gravity and K constant, and then laboratory values are a little bit below that, and then the coding I do a little bit lower is calculating the electric field, and then giving that as a vector. Oh, yeah. And then on the right, we have applying that vector to all points along that line. And then below that, just does the arrows showing off the forces. Then that comes into here. We can see the little green charges are the individual electric forces. The white is the sum total of all the electric forces, and the yellow is force of gravity. You can see the two sum arrows have equal magnitude, forces of balance, and the object is in static equilibrium. And then we have the charge I calculated as 5.2 times 10 to the negative 9th coulombs on each piece of tape. All right, and then so we had to make a few assumptions for this lab. The first one was we assumed that the two tapes would have the exact same charge since they're paired the exact same way, which isn't accurate as they were charged using friction to actually when we physically pulled apart the piece of tape, which like the force used very heavily. So it's not a great metric. However, over the large enough area of the tape, we can assume it'll become relatively constant, so we can compare them to each other relatively accurately. The second, we discounted variations of the height of the tape and just assumed that the value was 3 centimeters, because as you look back to our lab images, you can see that it's a parabola shape on top, and so obviously larger distance, less electric force in the center, but more on the sides. However, we're only looking at net force, so we assumed a constant distance and basically just took the average of it. So it accounts for some parts being higher and some being lower. Then for the what if and what does it mean section, what are the differences between treating this as a point line charge? If we only treat it as a point charge, it'd be the same as last time. All the charge is a singular spot in the tape, and then on the one tape above it, only using y components, not counting variations between atoms in the x and y directions. And how does this change the numbers? I got, before it was 9 times 10 to the negative 9th coulombs, or 9.2 was my numbers for last lab, and now it is 5.2. And why are these different? We have not just interactions directly above each other, but interactions side to side, which is more accurate as that is occurring constantly in the real world. All electrons will interact with all other ones, leading to this lab being the more accurate number of that 5.2 times 10 to the negative 9th. Thank you.